Multiple linear regression. Multiple linear regression, often abbreviated as MLR, extends the concept of simple linear regression when the dependent variable y depends on multiple independent variables which can range from x1, x2 until, let's say, k, when k independent variables determine the value of y. The functional relationship is restricted to linear relationship of order 1, and it is given by y equals to beta naught plus beta 1 x1 plus beta 2 x2 plus until we reach beta k xk plus our regular error term epsilon. Now the correlation coefficient rho is partial correlation coefficient, and it is determined for every pair of y with x1, y with x2, y with x3, and so on, to measure the degree of association between two variables while controlling for the effect of the other variables. On the other hand, betas are now referred to as the partial regression coefficients, which essentially implies that while holding all other x constant, what is the contribution of x1 in the determination of y is specified by beta 1, and we can do it, calculate the partial regression coefficient for each of the x. Unlike a straight line in SLR, the regression equation represents a hyperplane in a k-dimensional space. We can visualize a two-dimensional hyperplane, which is a plane which is like a sheet of paper. So here we have x1 and x2 determining y. So it represents a plane suspended in this three-dimensional space, where the beta 1 represents the slope with respect to x1 and beta 2 represents the slope with respect to x2, and the errors are either above the surface or below the surface, and they are of course perpendicular to the xy plane. We estimate the value of y using the regression function, and it is called as the y conditional on x specified by y hat, or expected value of y given x1, x2, x3, x4 until xk. Now with this point estimate, we can compute the interval estimate of y. This can be read from any statistical software. We do not bother about the formula and the computation of these values manually. And once we determine the value of y, we look at the reliability of the independent variables, and we remove any insignificant independent variables from the model and recompute the value of y and the other associated statistics to arrive at a reliable overall model. We may also have to standardize the independent variables if the scales of measurement of different x is very different. For example, let's say the values of age may range from 1 to 100, but the income can range from $20,000 to a couple $1 million. Now, when we build the model, the values of income are so high compared to age that they may simply reduce the age dimension as a spurious noise in the data. So to build the model, we bring both of them to the same scale. Z transform is a very common transform, but depending upon the requirement and the nature of the data, we may use other forms of standardization like log transform, log normal transform, etc. So these are the other things that we take into account while building the MLR. The overall model is evaluated using R square, and it is computed using the partial correlation coefficients of the individual variables, and the R square is always greater than the individual correlation coefficients. Often the correlation coefficient is misleading if there is another confounding variable related to both variables. So we may have to look out for those confounding variables while building these models. Example, a relationship between income and consumption may be misleading unless we control for the wealth variable. Somebody might have a very low income with very huge wealth. That person's behavior and spending pattern will be much different than somebody who is making, let's say, double the income but no wealth at all. The significance of R square is computed using the ANOVA test. Now, in the MLR, we have another kind of challenge which we don't see in the simple linear regression, is that if we keep on adding new variables to the model, even if those variables are spurious random noises, the R square will keep on increasing as more and more independent variables are added to the model. So this is a problem of the inflation of R square in multiple linear regression models. So to correct for that inflation, we use an adjusted R square, which penalizes more than necessary variables in the model. For a MLR to be significant, all t-tests, ANOVA tests, need to be significant. If any of them are not significant, our model is not reproducible and unreliable.